Good morning, everybody, and thank you for joining us. Today's webinar is on improved analysis of seawater using Combustion TOC, and is given by Christina Mason, Applications Chemist at Teledyne Tekmar. Christina will be answering questions at the end, so feel free to submit your questions using the Q&A feature throughout the presentation. This webinar is also being recorded and will be uploaded to our website in approximately a week. I'm going to go ahead and turn it over to Christina.
Good morning, everybody, and thank you for joining me. Today we're going to talk about analyzing seawater and saltwater using Combustion TOC. So the presentation is called Improved Analysis of Seawater Using Combustion TOC. And if you have any questions along the way, please type them in and I'll get to them at the end of the presentation. So I want to talk a little bit about 5310B and the EPA method 415.1. Both of these methods regulate how we analyze for TOC or total organic carbon. Total organic carbon is super important when you're analyzing seawater because we want to avoid pollution getting into our ocean water and into other streams. So if you have a large quantity of TOC in your samples, then that's an indication of organic pollution that's going to leak into our ocean water, which is ultimately going to increase the oxygen demanding load, and that's going to harm our fish and our living creatures in our water. For this process, it's required that the inorganic carbon is removed, and that's your carbonates and your bicarbonates, because that's not part of the oxygen demand. So I'm going to start with talking a little bit about 5310B, and then I will get into 415.1. and then we will talk about the actual salt samples that I analyzed for this presentation. So we'll start with 5310B. It's a standard method for total organic carbon, or TOC. First, the method requires that inorganic carbon must be removed. And like I previously stated, it's because the sodium bicarbonate and the sodium carbonate does not increase the potential oxygen demanding load of organic material. So it's removed. And then what you're left with is the organic carbon, and this is oxidized, and that produces CO2, your carbon dioxide. And then that is going to be measured with NDIR, which is the non-dispersive infrared detector. 5310 also requires that precision is measured, and I'll get into that throughout the presentation so that everybody knows the equations that are necessary. Just some things to remember before you start calibrating or even taking in samples is that everything needs to be clean of other contamination. So it's important to clean the glassware that's on your TOC unit, and that would be the mist trap, the IC sparger, and then that also includes the 40 ml VOA vials that you put your samples in. And not only should everything be clean, but new septa on the vials as well. As well, in the reservoir, you're going to need organic carbon-free water, ultra-zero air or oxygen, and then finally 21% phosphoric acid to sparge out the inorganic. To make the phosphoric acid, you're going to need 94 milliliters of deionized water and 18 milliliters of the 85% phosphoric acid. And because it is done by weight, not by volume, that is the 21% acid. But 5310B requires that after every 10th analysis to analyze a blank and a laboratory control sample. So basically, after every 10 samples that you run, you should run a blank and then also a check standard to make sure your calibration is still holding true. And finally, as I mentioned before, demonstration of precision. And here I have the equation that should be used. And so for a single person who's injecting, or with our unit, it's a carousel, these are the differences that are allowed between two like samples. And I'll show you an example of that as we go. So that's a quick summary of 5310B. I'm going to get into 415.1. They're very similar in nature, and I'll talk more about samples as we progress. 415.1, these are some of the sample types that are used to be measured, and this is going to include natural sugars, mercaptans, oils, cellulose fibers, and oily matters absorbed on silt particles. And we can also use this for salt water. So if you're storing samples, it's important to remember some things. First of all, if you can store it in glass, it's always preferable. Plastic is not as ideal. And if you're preserving your samples for more than 2 hours, you should preserve with acid. Store your samples in a cool area, away from sunlight and atmospheric oxygen, so that everything is preserved as they are. This method also requires that the inorganic carbon to be sparged, and that calibration is performed with KHP. And just like 5310B, you should analyze blank solutions. And your blank solution for both 5310B and 415.1 should be the same water source as you use to prepare your standards. So this is an overview of your 5310B and 415.1. And so when we designed the loadings, we went around and asked different laboratories what they really needed in a unit, and we came up with the Lodix. The Lodix is economical, it's easy to use, it's got shorter run times, so you can get more samples analyzed. It's super easy to maintain. You can add samples in, you can delete them, and you can import and export with the lens system. So here's the Lodix. Here's a picture of it. You can see it has a flow-through detector. And you can't see it in the picture, but there's a water reservoir that's awesome for rinsing after salty samples so that your salt doesn't build up as quick on your catalyst. It's easy to change your combustion tube, and you can run 30 samples at a time. And everybody who runs samples that are high in salt know that salt has the capability of blocking up ports and valves. So we took out for this unit the 7-port valve. There's no syringe mechanisms and pumpers. There's no more of the replacement needles that are expensive. And this all helps to make a unit cheaper to maintain, and also a unit that does well with wastewater samples and saltwater samples. So now that we've talked about the unit and 5310B and 415.1, we can talk more about how to analyze the salt samples. So first I started with the calibration that was from 0 to 100 ppm. So to make I first made a 1000 ppmc organic carbon standard, and I did this with 2.1254 grams of KHP, and I put that into 1 liter of deionized water. And I let that stir for a good couple hours so that everything is degassed, there's no bubbles, and everything is completely dissolved. So after making the 1000 ppm, I made a 100 from that. And then I also made a 0, a 1, a 5, a 10, a 25, 50, and 100. And that was my calibration. So you can see here on my calibration screen, it's linear, it's 0.9998. And that was the curve that we used to analyze the salt samples. So here is the points that I use. Like I said, 0, 1, 5, 10, 25, 50, and 100. And then again, R squared of 0.99981. And the only difference I did for the method was change the carrier gas delay. So I have the default method here and the salt method. In both units, it's a set sample loop. Like I said, there's no more needles, there's no more 7-port valves. It just keeps less things to get blocked with salt. You can also don't have the expensive parts to replace. So both of these methods are using a 0.5 milliliter sample loop. So the only thing that needed change is the carrier gas delay. And you can see that the default is set at 680. The acid volume is only 0.2 milliliters. The carrier gas delay is 60 seconds. And the sparge time is 60 seconds. On the salt method, the furnace temperature still stays at 680. So a lower temperature at 680 instead of 750 helps that combustion tube without solidifying the salt as much. The acid volume is at 0.2. The carrier gas delay is at 120 seconds instead of 60 seconds. And the sparge time is still 60 seconds. So to change this method, it's easy to do. All you have to do is go into your configuration screen, which I will show you, and click on your method, change your carrier gas delay time, and save it, and you are done. And with this method, you can also run other samples as well. So if you're a laboratory that's running salt method, salt samples and wastewater samples, you don't have to you can run them all with the 120-second carrier gas delay. So the way that I set the combustion tubes, or the default, is with 1/4 gram of quartz wool, 17 grams of catalyst, and 3 grams of the quartz beads. And I'll show you a picture. It's on the left-hand side. And as you can see, there is the quartz wool, and then the catalyst, and then the beads on top. And then for the sea salt, it's very similar. It's 1/4 gram of the quartz wool, 17 grams of the catalyst, and then a platinum screen and a quartz retain ring. And I will show you in the picture here. Very similar. The only difference here is that with the platinum screen and the quartz retain ring, that it catches the salt so that you can continue to run samples, but there's something there to absorb the salt so it doesn't attach to your catalyst, and you can still continue to get more runs out of it. So just to go over it again, because I know this is something that is important, is that they're both the same amount of catalyst. It's just instead of the quartz beads, you're having the platinum screen and the quartz retain ring. And there is another picture. The one on the right is for sea salt, and the one on the left is for the default. So the calibration, as I previously said, was 0 to 100 ppm. And then we made our check standard to 25, about right in the middle, a little bit lower. So there's our data for the first day that we ran. We ran a DI water just to make sure everything's cleaned up, and then a check standard. And then our salt was 3.5%. So I made a 25 check standard, and then I added what was with 3.5% salt, and the water was. And you can see that the check standards, the RSDs are well under 5%. Even the salt samples are well under 5%. With the unit, that's about 200 milliliters go into it, so that means about 200 milliliters come out of the vent. So when you're doing a leak check, you can take your standard flow meter and put it out the vent to the back and verify that there's 200 milliliters going out of the unit and into the unit. And this will come in handy throughout if you're running lots of salt, so you can tell if you've got a blockage or if you have a leak or anything that's not quite acting correctly. So this is day one. Obviously, everything is running smooth. 200 milliliters flowing in and 200 milliliters flowing out. There's no blockages or anything like that. So this is after 20 samples, and then this is after 160 samples. And this is 160 samples of running nothing but 3.5% salt. And you can see that the percent RSDs are still looking good. They're less than 5%. All the check standards are passing. One thing to keep in mind that with salt, sometimes you do need to do more rinses. So when I was making up a new check standard, I would just run a couple DI waters through the unit, make sure that the counts looked good, they were coming down low, and by low I mean less than 100 ABS. And then after running about 3 DI waters, I would run my schedule again, which is the check standards and the 10 salts. And as you can see with the study, we also ran a check standard after every 10 samples, just like 5310B and 415 asked of you to do. So this is after 180 salt samples, and you can see that there's clearly something not right. So we went from everything passing at 160 samples, check standards look good, to your check standards not passing, and some of the RSDs are getting high. And by the end of the schedule, our check standard has a 20% RSD. So you can tell here that something's not quite right. In addition to check standards not passing, as I mentioned earlier, your flow should be about 200 going in, 200 coming out. Well, by the end of this schedule, only 170 milliliters was flowing through the unit. So if 200 is going in, 170 is only coming out, you can tell there's obviously a blockage in the unit, which would also explain why our check standards are not passing and the RSDs are high. So I took the combustion tube out of the unit, and let's look at it before. So here's what it looked like before. Everything is see-through, transparent, nothing's etched. Everything, the callus is nice and dark, looks very healthy. Here's our combustion tube after 180 samples have been ran through it. And you can see that on the very top of the combustion tube that there is like a yellow salt block, but by the end of the combustion tube, the callus looks brand new. So with that, and we'll go back to the original picture, with the retain ring on top, it catches any salt that could damage your catalyst. So if you remove that salt blockage, your callus on the bottom is still healthy and it's usable. You just have to be very careful that you don't cut yourself on the quartz combustion tube because it is breakable and you can get hurt with it. In addition to running or changing the combustion tube, at the bottom of the combustion tube there are fittings, and it's good to make sure that those are cleaned out and they don't have any salt that might have blocked it. I didn't have any issues when I ran mine, but I did take it out and look at it and make sure that everything looked as it should. Look for anything else that might be wrong, any salt that could be someplace else. And then finally, if you put a new combustion tube in it, verify that you have 200 milliliters going in and 200 milliliters going out. and that you don't have any blockages anywhere. So with the Lodix, we were capable of running about 170 salt samples through it before we really had to take the combustion tube out, replace it, and put another one in. But if you are a laboratory that's analyzing salt water and wastewater and a variety of things, you might not necessarily only be having a calibration range from 0 to 100. The Lodix has a flow-through detector, so you can do a broad range of a calibration. Here we have one that's 0 to 1,000. So if your salt waters have a lower calibration range that's necessary, and you have wastewater samples that need a larger calibration range, then this detector could be perfect for that. And we can also go up to 20,000 ppm, and I'll show that curve next. So here's the 0 to 1,000 ppm calibration curve with the RSDs and the points. And you can see that the RSDs look gray on the low end, they look good on the high end. So that is good for sample matrices of different kinds and different areas of detection. And then finally, this is the 0 to 20,000 that I mentioned in the last slide. You can, excuse me, the R squared value is 0.9999, and you can see the points that were used on the right-hand side. There's quite a few of them, and all of the RSDs are less than 5%, so everything is got a good RSD. It's a linear range. And this will help with a large increase of sample throughput with avoiding several methods and calibrations. So we analyzed our salt samples with a 0.5 mil injection loop. We produced a calibration from 0 to 1,000, and then finally a calibration to 0 to 20,000, all using the same method and using the same injection volume. So I mentioned before we analyzed the salt samples with 5310B, and the 5310B asks for precision between your samples. And so the equation is on the left-hand side of the slide. It's 0.027x plus 0.29, and this is the operation for a single operator, this is the precision that we like to see. And then for this test, we ran a calibration from 0.5 to 10, and the R squared was 0.999. The concentration we used for this test was 0.5 ppm, and the single operated precision is 0.302. So 0.302 is what we need to see between the injections to be considered precise. So in the next slide, we'll show you the data for that. We also did the method detection limit. 415.1 and 5310B does not ask for an MDL, but we went ahead and did it to demonstrate how low the Lodix can go. And the MDL here is 54 ppb. So on the right-hand side, there's a table that shows the sample. There's 7 samples that we analyzed in a row, and they're within 0.302 of one another. And then from that, we made our MDL, which is 54 ppb. And so this 0.5 to 10 is the same method that we used for 0 to 20,000. So that flow-through detector that the Lodix has is really given a broad range. We can go on the lower end, we can go on the higher end, but it's all with a 0.5 sample loop, and it gave us our 54 ppb MDLs. So this is our software. As I mentioned earlier, we had to change one of the parameters in our method, so I'm going to show you guys how to do that in the software. I'm going to go over the software as well. It's built to look kind of like an application that we're used to seeing in our everyday life, and so it's super easy to navigate. You don't need all the clicks to make a calibration or to edit anything. It's just an easy-to-use software. So here's our configuration screen. So if this is our home screen, you see the blue box is configuration. That's like our settings that we can change. And this is what it is when you open it up. If you click on method parameters, I will go back to our screen. It's going to open up this table. And all we have to do is change the carrier gas delay from 60 seconds to 120 seconds, and you'll be set up to analyze salt. But with this method, you can also analyze your wastewater samples. It's just going to give you more time to oxidize. So the bottom under advanced is where our method parameters hang out, as well as configuration in a screen, as well as method parameters. You can name your instrument, and then you can also put the unit into standby, which will help you save on gas. So it'll go into standby after 30 minutes, and if you want the furnace to cool down as well, you can also set that here. The configuration screen also has, you can export samples, you can auto print samples, and you can archive samples here. So if you need to export to your LIMS system after you run those salt samples, or there's wastewater samples, you can do that. Or if you're in a rush and you need to print off a report after your one sample gets done, you can do that here as well. It'll do it automatically. As well as auto exporting and auto printing and archiving. There's the corrective actions area here. And as we all know, sometimes analyzing salts can be kind of tricky, or wastewater. So if you need to get samples that are less than 5% RSD, or if you need a standard deviation at a certain point, you can come here and select it. And it'll run an extra sample or an extra replicate and kick out a replicate to get the RSDs that you need. So if you are running three replicates and you need a 5% RSD and your RSD comes out to be 7%, it'll delete out your outlier and it'll run another replicate and recalculate it so that your RSDs are less than the 5% that you require. And it can do this for samples, blanks, calibration standards, or check standards. As well as doing that for samples and blanks, if you run a check standard and it fails, and you don't want to waste the samples that you've already have on your sample conveyor, you can rinse and rerun. Then if board that check standard fails, you can board immediately, or you can continue on failures. So this is just to help with the samples that are hard to oxidize. You know, sometimes you get a bad replicate for your salts, your wastewaters, and this will help to get those RSDs that we need. And then, as I mentioned before, the Advanced tab is for your method parameters, and then the System Export and System Import is there, so that if you need to take all the information that's on this computer with all your calibration, reports, sample data, you can put it on another computer very easily. This is our calibration curve. So for the salts that we ran, it was from 0 to 100. You can do the 8-point curve in less than 2 hours. It takes about 13 to 15 minutes a triplicate. Sometimes there's samples that are in the 20,000 ppm range are going to take longer because it takes longer for your sample to come back down to its baseline, but it's about 13 to 15 minutes for a triplicate. It only takes about 1 minute to make the calibration screen in your software, so everything is streamlined to be quick and easy. As well, for the calibration editor, as you can take your points out and adjust your blank, you can choose if your samples need to be calculated off the blank or the y-intercept. So I stated before that 5310B and 415 both need a blank analyzed. So if you select it to analyze a blank, it'll save that information right here in your calibration editor. However, if you choose not to use that blank, you can also use the y-intercept. This is the sample screen. So this is where all of our salt samples were ran. As you can see, it says seawater 1, 2, and 3. And then in the bottom right-hand corner, these are what the peaks that are our samples, and this is the flow-through detector. So you can watch the sample oxidize and the peak go up and then come back down to the baseline. So there aren't any more of the blocks or the sample just coming out. You can actually watch it oxidize and go through the instrument with the new detector that this unit has. So not only does this detector have the wide calibration range, but it's also a flow-through. As I mentioned before, there's the outlier deletion, so you can either go off of %RSD and or the standard deviation. You can add and delete samples, so if you need to add a priority sample, you can right-click and add it in. And then there's the real-time viewing of the analytical data, like I mentioned in the right-hand corner. Okay, as well, you can also print reports on the fly. So if you need to print off a sample as soon as it gets done running, you don't have to wait for the entire schedule to finish. And finally, maintenance, because as we all know, if we are running several samples that are high in salts, there's going to be some maintenance associated with it. And I personally think that the most important thing is how easy it is to change your combustion tube, which is why when we created this furnace, we wanted a furnace that's good for your catalyst, so you don't have to change it as much. And also, when you do have to change it, it's super easy to do. So this is our furnace right here, and there's a peak block on top of your combustion tube. And there are 2 screws that hold that on. So you just unscrew the top 2 screws, and then there's the top of the combustion tube is there. It's easy to grab onto and pull out. Just make sure that it's cooled off completely first. So we made it so it's easy to pull out. And then when you're ready to put it back in, it just slides easily back in, and then you just put your 2 screws on top and you're done, you're good to go. So that's always an important thing when looking at combustion TOC is how easy to change a combustion tube. So it's easy to do here, and that helps with the longer catalyst life because it's not pressurized, it is a flow-through, and then like I said, the flow-through NDIR for that broad range of calibration. Also, with running salts, lots of rinses are nice. So you can run a rinse, or you can run a DI water. And if you run a rinse, it comes right out of that water reservoir. And because it is pressurized, it saves it from any of the laboratory contamination. So you don't have to change it every day. You only have to change it when it's empty. So that's, the easy maintenance. Change your combustion tube easily. The water you don't have to change every day, and the catalyst is going to last much longer. So in conclusion, the Lodex is the ultimate solution for wastewater, surface water, groundwater, and importantly here, seawater, and other hard-to-oxidize matrices with an economical price to fit any budget and easily surpasses requirements for methods 5310B and 415.1. So are there any questions about the loadings in general or how to analyze saltwater? Please let me know.